is yours.
Thank you.
Well, first of all, hello everyone. Thank you for coming and thank you for having us here. So today we would like to present what we believe is an interesting example of how we can reuse projects that are part of the Kubernetes ecosystem to tackle some challenges that go beyond Kubernetes. And this is, for instance, in this case, the unified on-prem management of bare metal infrastructure for non-Kubernetes clusters via ClusterAPI, Metal3, and Virtual Kubelet. I'm Michele Gazzetti. I'm a software engineer part of IBM Research Europe, and today with me we have Michele Tagliani.
Hi everyone, I'm Michele Tagliani, and since yesterday I can call myself a software engineer and graduated from the University of Bologna. Thank you.
So, congratulations for this. And so, the presentation is organized as following. We are going to introduce the context and a bit of the challenges that we are facing with our infrastructure management. We are going to go through ClusterAPI and Metal3 that helps us in the management of Kubernetes clusters. We are going to see how and why we introduced the Virtual Kubelet for supporting non-Kubernetes clusters. Michele is going to go through a demo of HPC cluster management via ClusterAPI. We are going to conclude with some takeaways and next steps. So just for a bit of context, our team in IBM works on an initiative called Accelerated Discovery, where we explore the adoption of AI, HPC, cloud, and quantum to accelerate the discovery process. And this has a vast array of application from material discovery, geospatial observations, and so on. So we collaborate not just with developers, but with researchers with many different backgrounds from AI, HPC, chemistry, mathematics, and so on. And our team goal is to contribute to this initiative, but also manage the computing infrastructure for our colleagues. So we get requests for a very different and heterogeneous environment. We have the developer that requests Kubernetes clusters. We have the scientist that prefers the HPC cluster for AI training and simulation. And we have also hardware engineers that work on enabling next-gen hardware devices. And they need an isolated environment to test operating system, kernels, and so on. And something that they have in common is that they all want low-level access to the hardware. That is why most of our requests involve bare metal. And on the side, there is our team that needs to manage all this environment and these requests. So from an admin perspective, we need to manage multiple platforms, multiple infrastructure partitions, so set of physical servers. And what ended up is that we started using multiple management tools for our different clusters. And this created great complexity. So to alleviate this problem, we decided to explore the adoption of a unified cluster management layer that can handle both the Kubernetes scenario and the non-Kubernetes one. And we defined some of the requirements for this management tool based on our main pain points. And that was support for provisioning and the provisioning of hosts, dynamic scaling of our partition and our clusters. And this was very critical because most of the requests that we were getting were for GPU nodes. And this is the kind of resource that is quite limited inside our infrastructure. So we needed to be able to move servers between partitions based on our users' demands. It also needed to be lean and easy to support because we don't want the complexity to be moved at the management level. And we also wanted a universal interface for handling both the Kubernetes and non-Kubernetes scenarios. So we like to work on Kubernetes, so we said, okay, does Kubernetes define a way for managing infrastructure? And that's where we encountered ClusterAPI, that is a sub-project, part of Kubernetes, that simplifies the provisioning, upgrading, and operating of Kubernetes clusters. And one compelling aspect was the adoption of this modular design where it defines core abstractions and the complexity is delegated to pluggable components called providers. And in terms of ClusterAPI abstraction, the project takes the same approach that is generally used by Kubernetes for the management of workloads. So if in Kubernetes your unit of orchestration is the pod, and you can scale this to multiple pods using the replica sets, or adopt more complex features like rolling updates or rollbacks using the deployment, ClusterAPI takes the same approach, but it applies on the Kubernetes node management. So we have the machine, that is our Kubernetes node, that is the unit of orchestration. We scale this with the machine set, and we apply more complex feature with the machine deployment, so that we can scale different machine sets. We also have additional components necessary to run our cluster, like the control plane object, necessary to deploy our control plane nodes, and the cluster that aims at tying together all the objects that are related to the same Kubernetes installation. And what, again, was very compelling is that ClusterAPI does not take any assumptions on the Kubernetes distribution or the infrastructure where we want to run our cluster. And complexity is delegated to providers that take the general ClusterAPI objects and deploy the Kubernetes cluster on our infrastructure the way we want it. And to deploy a Kubernetes cluster, you need generally three types of provider. The infrastructure provider that provision the hosts and ensure that these are accessible. We have the Bootstrap provider that generates the initialization file that make a general host a Kubernetes node. So for instance, there is the installation of the kubelet that is used to run our pods. And we have also the control plane provider that handles the lifecycle management of control plane nodes. And this is a key component because the deployment of control plane nodes require additional steps like the generation of certificates, password to access the cluster, so it needs particular care. So they are all important, but I'm going to focus on the first two because they are key to understand how we handle the management of the non-Kubernetes deployments. So given our target scenario, the choice of Metal3 for the infrastructure provider was quite straightforward. And who was at the previous talk from Kashif? Let's see. Okay, so some of you might have a previous experience and have seen Metal3 before. So the project, something that is extremely useful as administrator is that it introduces an object called the bare metal host that is the Kubernetes representation of our physical server. So already with Metal3 we see that we have the first layer of abstraction where as an admin I don't have to interact with the physical server anymore, but I can manipulate a Kubernetes object to orchestrate my physical server. And here you have an example where you, for instance, you can set the image that you want to provision on your server, the configuration file that you want to use during the initialization step. Or you can also handle the power state of the cluster, so if it's power on, power off. And it also provides useful information about the state of our server, so we know at any time what is the state of our physical component. And another useful thing provided by Metal3 is that it acts as a bridge between the ClusterAPI abstract resources and the bare metal host management. So we can drive the state of our infrastructure. And this is done via the ClusterAPI provider Metal3. So starting from the image that we have seen before, ClusterAPI introduces many components and many objects, but the one that we had to interact the most was the Metal3 machine and a related template that is used to generate objects for multiple machines using the same starting point. And this object was key because it allowed us to define the network configuration that we wanted on our servers, passing a configuration file, and the image that we wanted to install on our physical server. And okay, so we have a way to set the operating system. We have a way to pass the network configuration, but this is only a piece of the puzzle. We need to install on our host all the service certificates, configuration file that make a host a Kubernetes node. And this is the task performed by the ClusterAPI Bootstrap Provider. This is one of many that you can have as part of ClusterAPI. And one of the useful elements provided by the ClusterAPI Bootstrap Provider is the kubeadm config objects that allows us to define the manifest to initialize our nodes. And one key component of this is the installation of the kubelet. So we see that from a physical server, we are moving to a Kubernetes representation. We are starting to customize our objects using Bootstrap providers. And in the case of kubeadm, one key step is the injection of all the commands to install a Kubernetes service like the kubelets. And under the hood, what we get from a kubeadm config object is a secret containing manifests like the cloud init, that these are the same manifests that you would use to configure your virtual machines. In this case, they are used also for our bare metal hosts. So this was extremely useful for us because we were approaching technologies that were already known in the team. And for the initialization part of the host, the provider injects kubeadm commands. That is a tool to initialize the node as part of a Kubernetes cluster. And something interesting is that this kubeadm config was used for both control plane and worker nodes for their initialization. So now we have all the components, for instance, for provision Kubernetes nodes. This is an example of worker nodes where using a machine deployment, we define our replicas. We're going to see an example in the demo. We can reference our Metal3 machine template with the operating system and network configuration. We can reference a kubeadm config with our initialization commands and steps. And some of the bare metal hosts will be selected, and Metal3 and ClusterAPI will work in unison to generate also the manifest that are used for the initialization of our host. And this is where we get our Kubernetes nodes. So all of this just to tell you that just with the ClusterAPI and Metal3, we meet many of the requirements that we were describing at the beginning. Because we can perform host provisioning, the provisioning and dynamically scale our clusters using machine deployment. We can use an easy and lean layer for this kind of management, because at the end of the day, ClusterAPI is a set of controllers that can be deployed using deployment manifests and useful CLI tools. The missing step that we had was this universal interface between Kubernetes and non-Kubernetes clusters. And so we thought about it and say, okay, ClusterAPI by design is for the management of Kubernetes clusters. Can we reuse what we have for non-Kubernetes scenarios? So what if we use the machine deployment, but instead of passing initialization files generated by a kubeadm provider that installs a kubelet, we pass a simple configuration example with just some credential, and for instance, we create a file on our host just to see if the configuration was used. So this is an example of what could happen. Here you see a machine deployment definition where we described 2 replicas. And we see that after 21 minutes, this is in a scaling up phase still. So we said, OK, maybe our hosts are still in a provisioning state. So we looked at the machines, and we say, OK, this makes sense. The phase is still in provisioning, as we were expecting. But if we look at the bare metal host, we see that this is the state we've provisioned. So just with this simple test, we validated some aspects. First of all, via CAPI and MetaCube, we can provision non-Kubernetes hosts because the state of our physical server that is represented by the bare metal host tells us that this is provisioned. And if we SSH and we enter the node and we look at the state, we see our files, we can use our credentials. So the process terminated successfully. But from a ClusterAPI perspective, the objects do not represent what we see at the bare metal host level. So in this case, the goal changes, and we need to just bridge this gap between ClusterAPI representation and the state of our non-Kubernetes server. So this is where we went back, look at the Kubernetes ecosystem, and see, OK, can we reuse something that is already available? And this is where we learned about the Virtual Kubelet. That is an open source project that is part of Kubernetes that provides a way to develop custom kubelet implementations. And this is generally used to take external services, like it could be a serverless endpoint, and present it in Kubernetes as a node. So we can apply the same process, but for the non-Kubernetes host, where we use the Virtual Kubelet to show that our host is available inside Kubernetes. ClusterAPI can see that this is available, and it can reconcile its state. And of course, with the Virtual Kubelet, we need a way to install it on our servers. And we take the same approach that it was described by the ClusterAPI Bootstrap Provider, but a key difference is that with this type of provider, we inject all the commands necessary to run our custom Virtual Kubelet. So we can customize the way we show our non-Kubernetes nodes to ClusterAPI. For instance, here you can see between the various steps, we can describe the files that we want on our host. We can also run the command to enable our Virtual Kubelet. And from a Kubernetes perspective, these non-Kubernetes nodes are seen as Kubernetes nodes, but they are tagged and configured to ensure that a workload will not be running on our host. And this was particularly important because we don't want our Kubernetes users to schedule workloads on our non-Kubernetes nodes, because this would break that level of isolation that we want between our partition, and we can create contention between workloads running on different clusters. Something that we do, for instance, is we taint the node, and by design, we don't allow workloads that are, even if they are forced to be scheduled, we don't run them on the node. So at the level of ClusterAPI, the admin can reuse the machine deployment, but instead of passing the kubeadmin config that is used to configure Kubernetes nodes, we can pass a virtual kubelet config where we install the virtual kubelet and we provide that level of bridging necessary for ClusterAPI to reconcile its resources. And this is how, under the hood, we provide that universal, we bridge that gap, and we define a way to manage both Kubernetes and non-Kubernetes nodes using the same interface that is ClusterAPI. So I leave the stage to Michele for a demo of this in action.
To show the adaptability of ClusterAPI extended by the Virtual Kubelet Bootstrap Provider, we decided to create a POC in which we want to provision a Slurm cluster using our solution. Why Slurm? Because it's one of the most effective workload managers, used by 65% of supercomputers in the top 500. Slurm consists of a slurmd daemon running on each compute node and a central slurmctld daemon operating on a management node, commonly referred to as the head node. The slurm daemon manages the resource locally and is responsible for the workload execution, while the slurm control daemon manages jobs and allocate resources within the work cluster. Our goal is to use ClusterAPI and the Virtual Kubelet to automatically configure bare metal machines with this setup. This will simplify the life for the admin, who will be able to use the convenient Kubernetes API. How do we do this? By producing some machine deployments. In order to provision some machines in ClusterAPI, you have to produce a machine deployment. A machine deployment is simply a manifest containing the characteristics of the machines to be managed via CAPI. Each machine represents a node in the machine deployment and has two main references that can be used to customize. The first one, the one in the bottom, is the infrastructure ref, which tells ClusterAPI the type of infrastructure it will manage. There are several infrastructure providers that allows CAPI to be adapted to a variety of infrastructure. There is IBM Cloud, JPC, AWS. But in our POC, we wanted to manage bare metal nodes, therefore we decided to use the Metal3 infrastructure provider. The config.ref is used to tell ClusterAPI how to configure the node so that it is visible within Kubernetes. This is, we are looking at a Kubernetes worker machine deployment, so there is the kubeadm config template, which is responsible for running the kubelet on that node. In order to provision the Slurm cluster, it was necessary to create a specific machine deployment for each of the node type, one for the head node and one for the worker node. As you can see, the only difference between the Kubernetes machine deployment and the Slurm worker machine deployment is the Bootstrap reference. In this case, we use the Virtual Kubelet config template in order to configure the node and make it visible inside the cluster. Before going into details of the Virtual Kubelet config template, let's analyze the Metal3 machine, which is common to both the Kubernetes and the Slurm cluster. As you can see, into the Metal3 machine template, there are only a few information needed that are about the operating system. Then the admin can use the data template reference to provide other setup like the network information or stuff like that. In this case, as can be seen for the slide, the Virtual Kubelet has been extended with a cloud conf designed to allow the automatic provisioning of a Slurm node. Our Bootstrap provider, so the ClusterAPI Bootstrap Provider Virtual Kubelet, adds to this configuration the ones needed to run the Virtual Kubelet and generate the cloud config secret that will be used by Metal3 to initialize the host. As you can see, there are configuration like the Slurm conf file, the user creation, all the commands that need to be run. Once the machine deployments for the two types of Slurm machines have been created, they can be applied using a simple kubectl apply command. From that point on, the administrator will be able to manage the Slurm cluster and the bare metal infrastructure as they were working with pods. I have a small video demo in which we have 12 bare metal nodes. 5 of them are already configured as Kubernetes, while the other 7 are going to be a Slurm cluster. So, the first thing, we look at the cluster, and we can see that it's comprised of 5 Kubernetes nodes. Now we can apply the machine deployment of the Slurm head, and then if we look at the machine deployment in our management cluster, we can see that there is the Slurm head machine deployment, but there are no replica. So we can simply scale the Slurm cluster using the kubectl scale command. All right. And now, if we look at the machine deployments and if we watch the machine deployments and the bare metal host, we can see that after a couple of minutes, one machine is selected and it will start the provisioning. while the Slurm head is provisioning, we can apply the same steps for the Slurm workers. In this case, we want to scale the number of Slurm workers to 6. We watch the machine deployment and the bare metal host. As we can see, the Slurm head is ready, while all the other nodes are in a provisioning state. While they are all provisioned, they will become ready in about 6 minutes, 8 minutes. Now, we have created the Slurm cluster. How we can check if it's working? We can log in into the head node using the sinfo command, which is a command used to watch which machines are part of the cluster. As you can see, the Slurm cluster is made of 6 nodes, as expected. And then we can try to use the cluster using a small hello world MPI hello world program that we have used. Yeah. Everything is working. We can see that every node is responding and it's running correctly. So we have used only some 2 commands, which are kubectl apply and kubectl scale, and we have a working Slurm cluster.
Thank you. And so, okay. So just some takeaways. We have seen that ClusterAPI and Metal3 brought us almost there. We had to just add some additional features to manage a completely different cluster, non-Kubernetes cluster like an HPC one. And something that was interesting is that no changes were necessary from the ClusterAPI and Metal3 project perspective to use this. We used the one provided by the community. And in general, if there is a lesson learned from our perspective, is that the Kubernetes community has tackled so many problems, so many challenges, because people used it in so many different ways. So if the main lesson would be to look at the Kubernetes ecosystems, even if it's something that it's not like one-to-one matching with your problem, and see if there are reusable solutions or at least inspiration that you can get from the community. So the ClusterAPI Bootstrap Provider for Virtual Kubelet is a project that is still in a POC phase, and we would like to get feedbacks, and if someone is interested and wants to collaborate, feel free to reach out. Something that you would like to improve is a particular design aspect of this approach, is that we need Kubernetes control planes for the virtual kubelets to register our non-Kubernetes nodes and let them be visible by ClusterAPI. And this means that at that level, we have both Kubernetes and non-Kubernetes nodes in the same cluster. So hosted control planes approaches where we define control planes just for non-Kubernetes nodes without wasting servers would definitely improve this approach. We also would like to explore some custom virtual kubelet that can provide like features that we believe would be very useful. For instance, the ability to debug your nodes, so get a shell inside your nodes and do some troubleshooting. That would be definitely interesting and useful even for non-Kubernetes nodes. And one of the big reasons why we started this was the support of HPC cluster. So we plan to integrate with the current Kubernetes project that aims at managing HPC clusters like Slinky. And so define interesting configuration where we could have pod and bare metal hosts working together for hosting HPC workloads. And of course, we would like to see if we can support different type of clusters like storage or reuse this for other target infrastructure. This thanks to the modularity of ClusterAPI that allow us to target different type of infrastructure like cloud. This is a link to the project. Feel free to take a look and reach out if you're interested. Thank you.
Thank you.
thank you, guys. We have some time for questions. So if you have any questions, please raise your hand. We'll pass by. All right.
Thanks. What feature would you like to have in the MetalCube that could help you with your own work with the CapV? Was there anything that you were missing?
To reach this goal, we didn't miss anything, but talking with the collaborators that would be interested in something along this line, providing management of also the network and the network layer for switches, for instance, isolating these partitions also on the network level, that would be something that would be extremely useful. That we didn't see a project in the ecosystem that would allow us to do this today.
There is now a proposal for that in MetalCube.
Exactly.
Yeah.
So
okay.
that would be useful.
Yeah.
I have a quick question on, you mentioned some developments on the Virtual Kubelet. So one of the things that is going on now is that there's a review of the Virtual Kubelet for the health of the project because of some doubts on the current maintainer support. Is this something that you think makes sense to maybe move some of these efforts to the core of this Virtual Kubelet, or are these specific things for your implementation or dependencies?
So for this enablement, we actually used the mock virtual kubelet provided by the project, because that was fitting in the sense that even if workloads were scheduled, these were not executed. Okay. So we didn't need much on top of what is already provided. The next phase of adoption or something like this would be to define a virtual kubelet that would target specific use cases. So there would be space probably there.
We'll come back to you, especially in this area of HPC. There's a couple of implementations in this area as well, so it will be interesting to see.
Yeah, no, we know that there are additional projects like Kubernetes that...
exactly, so this would be cool to sync.
Yeah.
Thank you, super interesting.
So I've got a question also about the virtual kubelet integrations. So in terms of monitoring and observability of components managed by virtual kubelet, do you look at enrichments within your provider or within your integration directly, or are you looking more towards potential enrichments to make visibility better within the deployment in the core component of virtual kubelet?
Both, I think, are useful. I think there is a view from the admin perspective that wants features like, for instance, the ability to debug the node. But it might be useful also from a user perspective where, okay, I can use Kubernetes as my universal point of view where I can see like both my clusters and see like where are my workloads running Kubernetes, non-Kubernetes, and I don't have to log in to different platforms to see what's happening. So there is much that can be done in terms of enablement here.
Is there any more questions?
All right, so then let's thank our speakers. We have some small gifts for you guys. Thank you for the effort. Can you pick? Yes.
Thank you.
So here you go. Thank you, guys.
Thank you.
Thank you.
Thank you.